In this video, we will discuss how to represent various angular or orbital angular momentum operators in spherical coordinate system. The reason is that angular momentum operators, they are generators of rotations in 3D space. So a spherical coordinate system is a natural choice for these operators. So let's begin with a discussion of spherical coordinate system. So let's say this is the Cartesian coordinate system, x, y, and z, and the spherical coordinate system, I can say if there is position vector r, its angle with z-axis as theta, and if I take its projection in the xy plane, then the angle of the projection with the x-axis is phi. Theta can be anywhere from 0 to pi, phi can be anywhere from 0 to 2 pi. With these two ranges, we can uniquely represent any direction, and the length of the vector is r, which is the third coordinate, and using these three coordinates, we can represent any point in 3D space. Now, there are a couple of important differences that we have to keep in mind when we are working with calculus in the spherical coordinate system. One of the important differences is that if we see the unit vectors in the Cartesian coordinate systems, for example, x hat, are we also represent it with I unit vector, and similarly j unit vector and k unit vector, they are constant. It means that if I have a point here in space or a point here in space, the unit vectors over here are like this is the x unit vector, this is the y unit vector, and this is the z unit vector. Similarly, for a point here, the x unit vector is parallel to this, y unit vector is still parallel to this, and z unit vector is parallel to this. And of course, all unit vectors by definition have a magnitude 1. So if these unit vectors are parallel to these, it means we have the same unit vectors, and it doesn't matter where the point is that we are representing. However, for a point which is being represented in spherical coordinate system, we can see the unit vectors change with the point. For example, for a point right here, the r unit vector is along this direction. Theta unit vector is along this direction because theta is increasing like this. Unit vector is always along a direction of increasing coordinate. So theta is increasing at this point like this. So theta unit vector is in this direction, and phi is increasing like this. So for a point here, phi is going into the board. So this is phi unit vector into the board. However, if I have a point somewhere here, then we see that r unit vector is like this. Clearly it's not this. Theta unit vector, because for this vector the angle theta is increasing in this direction, so theta unit vector is in this direction. Clearly this is not equal to this. And if this point also lies in the plane of this board, phi unit vector is still into the board. However, if I take a point somewhere over here, then r unit vector pointing away from the origin is like this. Theta unit vector coming from an angle from the z-axis is like this, and phi unit vector is like this. So all three vectors are perpendicular to each other, but an important difference between unit vectors in the spherical coordinate system and the Cartesian coordinate system is that these unit vectors are variable, which means that when we are taking derivatives, for example, I have to take derivative with respect to some parameter, and I have a quantity like this. Let's say there is some x unit vector and some function of position, let's say x, y, z, Let's just write this function of this parameter. So this gets out of the derivative and you only have to take derivative of this part. However, if we have to take, let's say, a derivative of a function like this, then I cannot take this out of the derivative operator. I have to use a product rule of derivative of this unit vector, this as it is, and then derivative of this multiply this, because this is a variable quantity. Okay, I will be providing the notes where we can easily work out the unit vectors from one coordinate system to another coordinate system. Right now, my interest is transforming the orbital angular momentum operators from the Cartesian coordinate system to the spherical coordinate system. Okay, so to do that, let's begin with the orbital angular momentum operator, which we can define from this equation. And if I open this up, I can write it like this: x operator, I unit vector, y operator, j unit vector, z operator, k unit vector, cross X operator, I, y, j, z, k. Now if I multiply these and then separate the x component of this operator, you can see that the x component is nothing but y pz minus zpy, and y is z hat px hat, and similarly nc is xpy minus px. And since we know that this operator p can also be given as minus iota h dot del, where this del operator is in Cartesian coordinate system partial x, partial y, partial z. So I could have come right from there, or maybe right over here I can substitute minus iota h bar partial z for this, and minus iota h bar partial y for this, and so on, and we can get there. And this y hat is just y, because position operator just gives the position of the particle. This minus iota h cut partial x partial z minus iota h bar partial y minus y partial x. Now I can convert these operators into spherical coordinate system if I know how to convert this y, z, partial z, etc. into spherical coordinate system. And let's see how we can do that. Let me draw the spherical coordinate system here again. X, y, z. So for a point here, this is, let's say, length r, this is angle theta. I take its projection, this is angle phi. So the x component of this vector is, if I project it here and then I project this along x-axis, we get x is equal to r. So this is r sine theta. And if I project this r sine theta to this axis, this is cos phi. Similarly, the y component of this point is r sine theta is this vector, and then I project it to here in terms of this angle phi. This is sine phi, and the z component is just the projection of this vector along z axis, which is r cos theta. So this part is easy. I now can replace x, y, z with these, and these positions will be converted to spherical coordinate system. However, I still have to find partial x, partial y, partial z to convert the angular momentum operator into spherical coordinate system. And I can do that by noting that partial x can be written as partial r by partial x, partial r, partial theta by partial x, partial theta, partial phi, partial x, partial phi. So with this chain rule, I can convert this partial x into the spherical coordinate system. All I need are these partial r by partial x, partial theta by partial x, partial phi by partial x. Now let's see how we can get these. Okay, so to get these, I can note that dx is sine theta cos phi dr plus r sine theta sine phi dy plus cos theta. And we can see it very easily because this is nothing but partial x by partial r. From here, partial x by partial r. This term is nothing but partial so dr, sorry, this is dx, this is dr, because this was partial x by partial r. Here I need partial x by partial theta from here, which is r cos theta cos phi d theta, and then I need partial x by partial phi. So partial x by partial phi of this is minus r sine theta sine phi d phi. So I can find this dx right from here, because from here I can find partial x by partial r, partial x by partial theta, partial x by partial phi. Similarly, I can write dy as sine theta sine phi dr plus r cos theta sine phi d theta plus r cos phi d phi, and dz as cos theta dr minus r sine theta d theta. And now I have three equations with the three quantities on this side, but my interest is to find partial r by partial x, etc. So for that, what I need is an expression for dr, d theta and d phi in terms of dx, dy, dz, because from there we can find these quantities. So for that, I can simply invert this very easily, and we can get dr sine theta cos phi dx, sine theta sine phi dy plus cos theta dz, d theta is 1 over r cos theta cos phi dx 1 over r cos theta sin phi dy minus 1 over r sin theta dz and d phi minus sin phi over r sin theta dx cos phi r sin theta dy. So if I now see these equation, this term is nothing but partial r by partial x. This is partial r by partial y. This is partial r by partial z. Similarly, we can identify this with the partial partial theta by partial x, partial theta by partial y, partial theta by partial z. Over here, this is partial phi by partial x, and this is partial phi by partial y, and in this case, partial phi by partial z is 0. So now I can substitute this partial r by partial x here, partial theta by partial x here, partial phi by partial x here, and we can get partial x as sin theta cos phi partial r plus 1 over r cos theta cos phi partial theta minus sin phi r sin theta partial. So this is partial x. Okay, so before proceeding, I actually quickly want to emphasize one point. Some of you might think that we could find partial x by partial r from here very easily, because it would simply be sin theta cos phi as we have written here. So why don't we just invert partial x by partial r to find partial r by partial x, instead of having to invert these three equations, and what we surprisingly see that partial r by partial x and partial x by partial r, they're actually both the same. The reason is this, that if we would have been in one-dimensional calculus, that we would have been able to do it, but not in more than one dimension. Because when we, let's say, has let me actually describe it, this point here. This is a small digression. So when we have, let's say, some function, so just as we had it here, like dx, dy, dz, in terms of something like this was partial x by partial r, partial, and here I had dr, d theta, d phi, so partial x by partial r, partial, so this would be partial x by partial theta, partial x by partial phi, and similarly the other two terms. So from here, to get to dr, d theta, d phi, in terms of dx, dz, dy, dz, I have to find the inverse of this matrix. So inverse of this matrix would come here, and the first term would be partial x by partial r by partial x. The next term would be partial r by partial y. The next term would be partial r by partial z. And we can see easily that if we would have one-dimensional case, that there is only dx and there is dr and only partial x by partial r, dr would simply be whatever the inverse here, but the inverse, since it's a one-dimensional matrix, the inverse of partial x by partial r would simply be partial r by partial x. So in 1D case, we could obtain the inverse simply by inverting this, but in 3D case, we have to find the inverse of this matrix where using the rules of matrix inversion, and whatever the quantities come here, the first is partial r by partial x and so on. So that's why we cannot simply find partial r by partial x by just inverting partial x by partial r. We have to find partial r by partial x, etc. from these equations. Okay, so having clarified this point, let me now go ahead. So just as we found expression for partial by partial x, partial, we can find expression for partial by partial y, we can find expression for partial by partial z, etc. And once we have these expressions, we can plug these expressions in these equations over here, and we can get Lx as iota h cut sine phi partial theta. The end result, fortunately, is not that frightening because it's small. So similarly, if you plug in for z partial x, etc., then Ly is iota h cut minus cos phi partial theta plus cotangent theta sine phi partial phi, and Lz is the easiest of all. It comes out to minus iota h bar partial phi. See here, I am finding this Lz by substituting for x partial y, etc. But we have already found Lz by definition from as a generator of rotation operator around the z-axis, and it was minus iota h bar partial y partial phi. Okay, so this is how we can convert the orbital angular momentum operator into the spherical coordinate system. Now, once we have Lx, Ly, Lz, all other orbital angular momentum operators can easily be found simply from Lx, Ly, and Lz. For example, I can find the raising and lowering operators by adding them. So plus is the raising operator, minus is the lowering operator. This is simply the complex superposition of Lx, Ly. If we add them together, I can find h bar iota phi partial theta plus minus iota cot theta partial phi. So this is how we can find these operators. Another operator which we will use frequently is actually this L square operator, which is nothing but Lx square, Ly square, Lz square. So I can find this operator by substituting the spherical form of Lx, Ly, and Lz here. But I would just like to, give you this little bit of a tip that if you want to find, let's say, Lx square, it's better, instead of working out this, you work it out by applying it to some arbitrary function of position psi. because now I can write it like this. This square is nothing but two operators in round. So this means that I should first apply this Lx operator, which is iota h bar. So there is an iota h bar here, so I'm combining both iota h bars in minus h bar squared sine phi partial theta plus cot theta cos phi. There is this partial by partial phi, and then this operator is applying on psi, so I can write it sine phi partial psi is a partial theta plus cot theta cos phi partial psi is a partial phi. So now we have to apply this one to this term wise. For example, this will be applicable to this. So these are two functions, one here, one here. So when this sine theta applies to this, so this is constant. So this simply gets out of this derivative, and we have minus h bar square sine square phi partial square sine the partial theta square. Now when this applies to this term, so there are potentially two functions of theta. So this is cot theta, and this psi is an arbitrary function of position. So theta could be inside this. So this is a constant for this operator. So I get sine phi this one, and that cos phi over here. But this partial theta has to apply to this cot theta partial phi. And we have to open it using product rule. Similarly, when this applies here, so this is out of this derivative, but this will apply on this as a product rule. And when this partial phi applies here, this you will have to use product rule on these two. So once you work out all of these terms, that is your Lx square. Similarly, we have to compute Ly square, Lz square, and put them all back here. And from this, we can find the expression for L square as minus h bar square 1 over sine theta partial theta sine theta partial theta. Because at the end you can just remove this sign that we had used here when you are combining and you only want the operator without sign. Plus plus 1 over sine square theta partial square partial phi square. So this is our L square operator. We can actually use the same approach if we want to, let's say, express other coordinates, other operators in spherical coordinate system. For example, this del operator, which is partial x plus partial y plus partial z. Of course, we will also have to use the spherical form for I, j, and k, but then we also substitute for partial x, y, and z in spherical coordinates, and we get this operator in spherical coordinates like this. Phi unit vector or sine phi partial phi. But the operator that we are going to use several times is what is called the Laplacian, which is essentially the del dot del or del square operator. And in Cartesian coordinates, it's partial square by partial x square, partial square by partial y square, and partial square by partial z square. Now, if we want to find this one in spherical coordinates, we have to evaluate this partial square by partial x square, just as we were evaluating this term. That it's better if you put a psi here and then apply this partial x successively in spherical coordinate and get whatever this term is. Similarly for these two, then combine all of them to find del square in spherical coordinate system. Okay, so this is how we obtain, we convert operators from Cartesian coordinates to spherical coordinate system using the expressions that we obtain for partial x, etc. And we will use these operators in the next lecture in finding the spherical harmonics and other properties of orbital angular momentum eigenfunctions. Thank you.